Good morning, good afternoon, and good evening, everyone, wherever you might be. So today we're going to be doing a little bit of exercises on derivatives and integrals of vector equations. So yeah, let's just hop right into it. So for number one, we're being asked to consider the following vector equation. Okay. And this is going to be R of t with these component functions. So this is in 2D, right? Because it only has two components. And here we're being asked to find R prime of t. And so how do we do that? Well, we basically take the derivative of both components. And so the derivative of 4t minus 5, since that's the first one, it's just going to be 4. And the derivative of t squared plus 2 is just 2t. And so our R prime of t is going to be 4 2t. So here we're analyzing so here by taking the derivative, we can analyze its, what we call direction, or its rate of change, right? If this were our position, say we use this vector in a graph, here we'll be able to analyze what point are we at, or our distance. And here we'll be able to analyze what our velocity or speed is at that point. So that's the basic idea. So let me just quickly type that in. 4 comma 2t. So you figure out. Nice. Next thing here is we're being asked to sketch the curve together with the position vector and its tangent vector, given t is equal to -1. So we want to sketch the curve of both position vector. So position vector is again what I previously mentioned. It's this thing here, R of t. So that's position vector. So okay, it's a good thing they mentioned it in the exercises. And tangent vector. So this one is R prime of t. And here we're actually given a t value, -1. So how do we do that? Well, we just plug in t equals -1 so that we can find the corresponding points. So R of 1 is what? 4 minus 5, so or no, 4 times -1 minus 5. So that's -4 minus 5. Then we have -1 squared plus 2. So here I'm just plugging in. And we get -4 minus 5, so we get -9. And here we get 3. -1 multiplied by itself, it's +1. Add that to 2, we get 3. Then we plug in for R prime, or for our derivative. And so here that's always going to be a 4, and this is going to be -2. because we multiplied 2 by -1. So now how do we sketch this? Well, since r of 1 is our position vector, we can say r of 1 starts at the origin. So it starts from the point 0, 0, and it's going to go all the way to -9, 3. Or at least it has that slope, right? So let's quickly do that. So for -9, so it's going to go -9 to the left, or 9 to the left. So I might redraw this thing. -9 to the left, and 3 above. So most likely we have it here. So it's going to be a vector pointing there, and this is r of 1. I hope I'm right. Yeah, hopefully. And then now its tangent is 4, -2. So it's going to start here. That's where it's going to start. And from here, I'm going to move 4 to the right, right? Because this is my change in x, my change in y. So I'm moving 4 to the right. So let's say this is 4. So let's say this is -5, 4 to the right, and 2 down. And so let's say this is 1. Kind of intersects in a way, which is funny. So maybe like here. Yeah. So I guess it's maybe gonna go maybe like that, right? I'm gonna check if that's correct though. Yeah. And I'm gonna show the sketch that because here we are supposed to pick what sketch it is. Okay, let me just quickly check. Um, hmm. Oh, I just realized we could have also done it. We could have also gotten the parametric equations. Oh, and then made a curve out of that so that we can actually find the actual path because it's in 2D. So we could have also done that to find the vertex and everything. So that's unique. What else? Oh, yeah, we could have done that. Uh, mm, just double checking. R prime. Oh, okay. Yeah, so another way we will be able to actually sketch the position vector and the tangent vector, or at least a bit more accurately than the one I did, is to actually find the curve or the path at which the particle or the object is moving, or the point. So we could have also done parameterize this thing. So we make parametric equations out of this, right? Because these are x and y. This gives us a corresponding x and y value. And then we could have isolated one of them, and we made like a function of y of x. So we put y in terms of x. So we could say, oh, I could isolate t here, right? And then I could plug in my y, or my t, but it's x. And then that's an equation that I have. And here we know it's actually a parabola because it's in the second degree. So that's just one other thing we could have done. But either way, I think it's fine. Without knowing the actual path, yeah, we should be pretty chill. So yeah, let me just see if I got it. Um, let's hit submit, see what happens. Uh, okay, we got it. Yeah, so it's basically, this is the more accurate curve. So here it's a parabola. Yeah, one thing I'm working on is graphing these things. Uh, yeah, so this is a more accurate graph. So here we can see that the position vector is pointing here. So kind of like this. And the direction vector or the derivative is this thing. And well, based on here, we can see that it's traveling this way. How do we know? Well, we keep plugging in points and see where it leads to. So let's say R of 1 leads to this point, then we check R of 2 where it leads to next, right? And that will help us, or that will help us determine what's the direction, where is it going. Okay, cool. Now let's move on to our next example here. So again, we do the same thing. So again, we consider a vector equation. Let me just quickly do that. And in this vector equation, well, we're given this one. R of t is e to the 8t I plus e to the 4tj. So this is natural logarithms, or no, natural exponents. Yeah, I tend to mix them a lot because they're both natural. And here we're being asked to find, again, its derivative. And so how do we do that again? Well, we take the derivative. So here another calc 2 thing. So we take derivative, well, we say, oh, we can actually equate this to e to the 8t, e to the 4t. So just something to derive this from. Here I'm just converting it to vector form because I want to do it that way. So okay, let me just do it step by step. So the derivative of the x component, or this function, this component function is, well, we do chain rule. So e to the 8t, and then we take the derivative of what's inside that e function. And here we get 8. So 8e to the 8t. That's it. Then e to the 4t, you guessed it, it's the same thing. 4e to the 4t. And there we have it. R prime of t has these components. And we could also put them in ij. Oh, I put so we could put them in either way. Either format is okay. But I prefer this format, so I'm gonna write it that way. Let me see. So we get 8e to the 8t. Then we get 4e to the 4t. Yep. And that should be it. See if we got it. Hope we did. Okay. And again, we're being asked to sketch. So I'm just gonna copy paste. So we're being asked to sketch the position and tangent vector given a t-value. I'm gonna quickly paste. And I'll just change this to oh, okay. It's not working. Okay. There we go. When t is 0. So again, we want to plug in the t-value. So we plug in t equals 0 for both the position and tangent vector. So r of 0 will give me something. So oh, they're both 1. Because I get e to the 8 times 0, e to the 4 times 0, and then I get e to the 0, and e to the 0. And e to the 0 is just 1 and 1. And so that's my position vector at t equals 0. And at the derivative, the rate is going to be 8 times e to the 8 times 0 and 4 times e to the 4 times 0. And well, this is just going to give me 8 and 4. And then here we can graph this now, right? So if you want to graph this thing, well, again, I'm going to draw a Cartesian plane, the xy plane to be specific. And then I'm going to look at my options. So I have options here. But okay, first I'm going to draw my position vector. So my position vector goes to 1, 1. So I'm going to say this is 1 and this is 1. And then from this point, I'm going to draw my tangent vector. And my tangent vector here is basically a slope because it's in 2D. So this is x, change in x and change in y. I can rewrite this to be a slope. So how do I do that? Well, actually, I don't even need to. I could say, okay, this is 4 over 8 because it's my change in y over my change in x, which is just my m, or my slope from a pre-calculus course. And I can even say, oh, this is just 1/2. So I could say, oh, this is 2 over 1. I could do that. But we don't really need to look into that. I could just say, okay, I'm gonna move 8 times to the right. I'm gonna move 4 times up. So that's what I'm doing. So I'm gonna say, again, I'm moving 8 times to the right. Well, to be more specific, this should be 9. And then I'm moving 4 times up. So if I move 4 times up, this is 5. So I would get something like this. And that's my r prime. Now, finding the actual curve itself, well, we could parameterize this again. We could say x is 8 e to the 8t, y is e to the 4t. I could isolate x in terms of t. How would I do that? Well, I would say I would use a natural log to cancel that e. I would get 8t equals ln x. And then I would just divide it by 8. So 1/8 ln x. And then I would plug that in here. But again, it's a complicated function, so I wouldn't really do it that way. Yeah, I could. And I would graph that thing. But I don't really need to. So if I were to choose a graph that's pretty close to what I just said, well, okay, I have two things here, which is kind of funny. Oh. Oh, yeah, so I moved all the way to 9. 6, 7, 8, 9. And this one's all the way to 5, right? Yeah, it should be all the way to 5. So I'm guessing this one's probably it. I'm just guessing. Because the others, well, I move 1 or here. Yeah, I move 1, so that's good. Here I move 1 again. Here I move 1 again. So all graphs are good. Here I'm just doing process of elimination. Then from here I move all the way to 5. I move all the way to, so this one's too large. So it's probably not this. I should move all the way to 8 to the right. 8 times, so I have to be at 9. Yeah, okay. I was just picking from the choices. Yeah, here I move all the way to 9. 9 to 9 when I go right, and when I go up, I move all the way to 5. So that should be it. I'm gonna hit submit, see what happens. Yep, you got it. So yeah, so it should be like this. And let me show a curve. Oh, what happened? Oh, you're all the way over here. Don't know why you went all the way over there. Yeah. So that's the graph, how it should look like. So this vector is my position vector, so it's this one. And this is my tangent vector. So it's that one. And see here, it goes to 9 and to 5. So here goes to 9 and to 5. So that's why, yeah, my drawing's not good. It's not in scale. But yeah, that's the idea. Okay, next example. So here we're being asked to find the derivative. So r prime of t of a vector function. And so this vector function is um, r of t, which is equal to these components. So our x component, our y component, and our z component. Okay. Now we just take the derivative. So to take, yeah, here we just take derivative. So again, I'm just writing the steps. So if we take the derivative of this thing, well, we get negative e to the negative t. And if we take the derivative of this thing, well, we get 5 minus 3 t squared. And if we take the derivative of ln of t, well, here we get, if I believe, it should be 1 over t, right? Yeah. Derivative of a natural log. Yeah, it's 1 over t. And so I just combine it. So I get r prime of t. And I put everything in. And that's my answer. So I'm just gonna write this and see if I got it. Should be able to. Comma 5 minus 3t squared. Or no, 3t squared. Okay. I have 1 over t. And that should be it. Hit submit, see what happens. Okay. Next thing we want to do. Okay, that's that. Number 4. Here we want to find what we call a unit tangent vector. So this is basically taking the derivative and the length is 1, pretty much. Because a unit, that's what the unit means. Unit means 1 at the point. So here we want to find the unit tangent vector at the point with the given value. Of the parameter t. So our parameter here is t. So here's our vector function. So we're actually given a vector function, and it has 3 components this time. So we know this is in, okay, even the other example, here we have 3 components. So we know this is in 3D. So we have my x component, my y component, and my z component. Oh, that's cube. 3 cube, d cubed. Then this is squared. Just taking off my earphones. And yeah, those are my 3 components, and my condition, or my t, is at 4. So to find my unit tangent vector, I actually have a formula, which is, so to get a unit tangent vector, I need my derivative and the length of that thing. So I just need to use that formula. So I need to find r prime of t and its length. So r prime of t is again just taking derivatives of each of these. So the derivative of t squared minus 4t, we get 2t minus 4. The derivative of 1 plus 5t, that's 5. The derivative of 1 over 3 t cubed plus 1 over 2 t squared is 1 over, or no, I put down the 3, I get a 1, so I get t squared. Then I add that to something, to the derivative of this thing, so this is t. Yeah, it's just t, because 1/2 put the 2 down. This is 2 minus 1, so that's 2. And 2 over 2 is 1, so that's 2. There we go. So that's that. And then I now need to find its length. So I'm not gonna like put the formula in. So I'm actually gonna, okay, let me just do this. So if you want to get exactly at 4, then we need to modify our parameter a bit, make it 4. So our prime of 4 is going to be what? 2 times 4 is 8 minus 4, that's 4. 5, and 4 squared, that's 16, plus 4, that's 20. So that's that, and therefore my r prime of 4, so let's actually change this. Let's make it 4. So this is just the length of 4 squared, 5 squared, 20 squared. And this will give me some number that I don't know. So let me continue computing. So that's 16. Oh, 16 plus 25 plus 400, I believe. I hope I'm not right. I mean, I hope I'm not wrong. Yeah, so we have 400 plus 25 plus 16 is 441. Can we square root that? Oh, we can. So we get square root 441, which is just 21. So that's my length. And so yeah, now we can just find unit tangent vector. So this is just T of 4, which is actually I don't even need to do this. That's just the formula we have to use. So I'm just gonna plop it in. So we have r prime of 4 divided by its length. And so we have 1 over 21 multiplied to this vector, 4, 5, 20. And so this will give me 4 over 21, 5 over 21, 20 over 21. And this should have length 1. Do I know? Well, I can check it. So to check its length from the origin, well, I just do a distance formula. So I do this squared 5, and then the 20. And this should equal to 1, right? So let's see. Just to prove it works. I'm also trying to not doubt myself that it actually works. So we have 16 over 21 squared is 441. Here we have 25. And here we have 400. And I keep going. So I have 16 plus 25 plus 400. I get 441. And I get square root of 1. I get 1. So that's how you know that it's a unit vector, because it always has a length of 1. Whether it's a unit tangent vector or a unit vector, it's always going to be a vector with length or magnitude of 1. So yeah, that's that. That's my answer. So let me just plop that in. I was just worried, that's why I was checking. Because who knows, I might be saying the wrong things. Yeah. Okay, let me just hit submit, see what happens. Nice. Okay. Now we proceed to our next question. So here we're being asked to find parametric equations. For the tangent line. to some curve. What curve is it? Is the curve given? Curve is not given, but we have some parameters that are given, or some equations that were given. So we have given parametric equations. And we're also being specified at what point exactly is it. Yeah, so here we're given for x, we have t squared plus 1. For y, we have 6 squared t. For z, we have e to the t squared minus t. And our given point is 2, 6, 1. So how do we find parametric equations here? Well, for one, this is already a position vector, right? And I don't even need to point it out. Okay, maybe I need to point it out for myself. But this is already a position vector with these components. No, not z. E. Now what I can do here is take its derivative, right? So that I can find the velocity or the direction, right? So I need to find the direction because this, once I plug in a t, I get a position. So here I can easily find t. I just plug in one of these things. So I can plug in one of these things with one of these things. I could do that. So yeah. And I'll see which one exactly works and which one doesn't. So I could find a t that works for all of them. And then yeah, I could find the tangent line or the tangent vector. I could do that. And then once I find the tangent vector, I can now convert them to parametric equations. Why? Because for a parametric equations, what do I need? So it's similar to a line. I need a given point, which I already have, these ones. And I need a direction vector that's parallel. And so the way to do that is to get its derivative. And so I need a tangent vector. And to get that tangent vector, I just take its derivative here, get the tangent vector, get it, or get the, what do you call that? Yeah, get the exact direction vector at the corresponding t. So before I eternally, yeah, I'm gonna say everything. No, I'm gonna write everything. So translate to position vector. This is the easy stuff because this is already in itself a position vector. I plug in some time to this vector function. I get an ordered triple out of it. So that's done. Next, I find the t that gives me the initial point. And my initial point is already there. So this is 2, 6, 1. So how do I do that? Well, I can say, okay, t or x is equal to this thing, t squared plus 2, t squared plus 1. But this is also equal to 2. Right? Because there's also my x value. So I'm just going to equate those two. find the t out of it. So, okay, we see that 1 is equal to t squared, and t could be, what do you call this? T could be plus or minus 1, right? And so I'm going to try both of them to the next one. So here we have y equals 6 square root of t. We have 6 here, so I'm just going to equate them. So we have 6 equals 6 square root of t. I can divide both by 6, so I get 1 equals square root of t. And here, um, 1 works, but negative 1 doesn't, right? Okay, so this is the issue with doing square roots. Yeah, that's an issue. Yeah, we have this. Then we have either a positive one or a negative. And then here, let me think a bit. Here, if I plug in a 1, this works. If I plug in a negative 1, this doesn't work. But I could square both sides, and this will work. Because if I square both sides, well, I get t equals 1. And so we know that negative 1 here doesn't work. And if I try the last one, so it should work for all points. If it doesn't, then there's no point. There's no point in doing it anymore. I'm kidding. So here we have 1 equals z. Oh, this is on the exponent. So so here, what can I do? Well, I can do an ln e. And ln of 1, is basically 0. Ln of 1 is equal to 0. And so this is just t squared minus t. And I could add t to both sides. Or actually, I don't need to. I could just factor it out. So I get t minus 1. Then here I get, ooh. So I get equals 0. And I get t equals 1. If we try 0, that definitely doesn't work. If we try 1, well, here we can see it works for all of them. So t equals 1 works here, t equals 1 works here. Maybe I'll just do this just to separate them. So the t that works for all of them is t equals 1. Great, now we found that. Now we know t equals 1 works. Well, now I need to find the tangent vector at that point. So I need to find or what speed it's at, or what's the tangent vector, specifically at t equals 1. And so first to find the tangent vector, well, I have to take derivatives. So r prime of t. So I have to take derivatives of all components here. So I have 2t for my x component. For my y, I have, so this one, the derivative. So here I can say, oh, this is equal to 1/2, t to the 1/2. And here I can bring it down. So I get 6, 1/2 t, 1/2 minus 1. So that's negative 1/2. I can see, oh, this is a 3. This is t minus 1/2. Oh, this is 3. This is, let me see. This is 3 times 1 over t 1/2. And then that's just 3
1 over square root of t, and so that's just 3 square root of t, right? So that's that derivative. So we have 3 square root t. Yeah, so more on Calc 1 stuff, taking derivatives. And lastly, we have e t squared minus t. So we have this thing. This is all in the exponent. So this is going to give me, taking its derivative, I'm going to use chain rule. So I have this thing, and I do the chain rule on the inner function. And then this one's going to give me e t squared minus t. So that's done. Here is going to give me a 2t minus 1. So yet another tricky stuff here, but basically that's it. That's the derivative. So it's e t squared minus t times 2t minus 1. And then that's my vector, my tangent vector. I don't know if I can simplify this. I can't think of any way. Yeah. Or if I messed up, I don't. Yeah, if I messed up, then that's probably where I don't think so. Yeah, because I did change rule here. Um, yeah. I could also do a product rule, believe it or not. But that's way too messy, so I'm not gonna do that. Okay. Yeah, this looks fine. And then we get r prime at 1. So here I plug in 1 to 2. And so I get 2, I get 3, I get, okay, this one's 1 minus 1. So that's 0, e to the 0. So this gives me a 1. I wrote 0. This gives me a 1. And this gives me, what is this? 2 minus 1. That's 2 minus 1. So this 2 minus 1, that's 1. 1 times 1 is 1. So I get 1 here. And that's my tangent vector at that point. Okay. Now what do we have here? Well, we have our initial point and we have our direction parallel or our parallel vector or tangent vector. And so now we can find parametric equations. So let me just quickly do that. Okay, I have some tips here that I got, but basically it's this thing where we just have an x, a y, and a z, and we plug in the initial point at that time equals 0 in this case, and we also plug in its derivative. Then we just add the plus t thingy. So it's the same idea as constructing parametric equations of a line. Literally the same idea. So I'm gonna do that. So this is going to be x equals, so my initial point, so I have 2, 6, and 1. This is 2 plus, then my direction vector, so 2t. Then my y, so that's 6, 6 plus 3t. That's it. And my z, I have 1 plus 1t, so 1 plus t. And that's done. That's the parametric equations for the tangent line. The curve with, well, based on this position vector or these parametric equations and this specific initial point. So that's that. So let me just plop that in. Yes, I should. If I got it wrong, then sorry. If I got it right, then kudos. Okay, that's 1 plus t. Yeah, let me hit submit, see what happens. Okay, got it. Next. So same idea here. A bit complicated now because of the functions, the elementary functions. So here we find, shouldn't be that hard though. We just follow the same idea. Find, okay, why am I should just copy paste. Yeah, I'm not efficient. So let me quickly do that. Same idea. So we just, it's really, honestly, math is all about mathings. Um, okay, so let's, yeah. And then here you just copy my highlights. Oh, I forgot to state the givens. So the given is I have parametric equations, right? These are these guys. So we have a square root for my x. For my y, we have a natural log. So it's an elementary function of pre-calculus. And for my z, we have t. Oh, very simple. And for my initial points, we actually have 2 ln4. So ln4 is a number, and 1. And here we're being asked to again find parametric equations. So I'm just going to do what I did before. So yeah, just for practice, I'm going to walk through it, but feel free to skip. So we translate to position vector again. Um, so we get r of t, and we just basically plop this in. Ln t squared plus 3 and t. So just plop those in, done. Next thing, based on my notes, we find the t that gives the initial point. So here we find our t. That gives me this initial point. So what's my initial point? Well, it's 2 ln4 and 1. And what in the world is that? Well, I plug in what I know. So square root of t squared plus 3 is my x value. And that's just the same as 2. Okay, I'm trying to not mess up my square roots here. Okay, that's fine. That looks fine. Okay, and here we solve for t. So I can just uh put everything to the power of 2. So this gives me 4 t squared plus 3. I did that to eliminate the square root. And then I can subtract 3 to both sides. So I get 1 equals t squared. And I get the same thing again. So t is 1 and t is negative 1. Now we try doing it again for our y this time. So for our y, we see, oh, okay. So for our y, we have ln of t squared plus 3 is the same as ln4. And here again, we solve for t. So the way to do this is, we can put everything to the e, right? If we do that, well, we basically get t squared plus 3 equals 4. So essentially, we kind of don't need to do that. We can just cancel out the ln's and we're good. But yeah, that's the math behind it. You put an e because these are exponential functions, and ln is logarithmic functions. So that's a pre-calc class. And you'll notice, or they'll give you a proof that these two elementary functions are inverses of each other. So that means they cancel out if you were to ever use them algebraically. And so, oh, look at that. It's the same thing as this one. So that's funny. Well, yeah, so we get the same thing. Okay, cool. Now let's try z. Oh, look at that. t equals 1. Yeah, so I would say this is easier. So the only thing that works here is t equals 1. Okay, now we found our t. It's funny, it's the same thing here. Now we find our tangent vector again at t equals 1. So let's quickly do that. Oh, crap. I didn't put in blue. So here we find our tangent vector at t equals 1. And so we again have to take derivative um, of our vector function here. So what's the derivative of this thing? So, okay, these are the hard parts now. So the way to do this, well, at least from what I've been taught in a calc class, is to always get rid of the square roots. So I have to put in exponents. So this is the same as saying, okay, this is 1 to the power of 1/2 if we do a square root. And then now what I can do here is there's a chain root because I can take the derivative of the outer function and then do something with the inner. Multiply it by the derivative of the inner. So that's a chain rule. So I put the outer, so I do 1/2 of the same thing. 1/2 minus 1, so I get negative 1/2 here. And I multiply it by, so this is multiplication, not dot product. I multiply it by the derivative of this thing, which is just 2t. So what do I get? Well, if I continue, so I get 1/2. I can actually do this, 1/2 square root of t squared plus 3. Because it's a negative, so I put it down, the exponent becomes a positive, and then now I just turn it back into a square root as I won't be needing it anymore. I multiply it by the derivative, so that's 2t, and I can cancel out the 2. So I get this. So t over square root of t squared plus 3. That's my derivative. Okay, I was just double checking to see if that's right. I hope that's right. Okay, so that's that. And now if we plot this in, done. Uh, now we take the derivative of the y component function. I don't know how to name it, but the y component function. So that's the derivative of ln t squared plus 3. Now notice if we take the derivative of this thing, it's the same as that previous one, ln of t, which is 1/t. And then we do a chain rule. So derivative of t, so that's 1. So we have 1/t times 1, which is just 1/t. Here in this case, it's the same thing. So we do 1 over the inner function, and then we do a chain rule. So we take the derivative of this thing, which will give us 2t. Done. So this is 2t over t squared plus 3. So yeah. Wow, I'm going back to calculus 1. And lastly, t. Oh, that's just 1. That's it. Okay, now we plug in 1 for t, and we just solve it normally. So we have 1 over square root of 3. Oh, crap. What am I doing? Or no, not 1 over square root of 3. This is 1 squared, 1 plus 3, 4. So this is 1/2. And then this is 2 over, what's this? 4. 2 over 4. Again, a 1/2. I don't plug in anything in the z, so that's just 1. That's my tangent vector. And from there, I can find parametric equations. So let me quickly do that. Because we have our initial point and we have our direction vector here. So that's going to be x, oh, what's that? X equals my initial point. So we have 2 plus 1/2 of t. Then we have y equals ln 4. I keep forgetting. We add that to 1/2 of t again. And then we have z, which is 1 plus t. Or 1 plus 1t. So that's just, again, 1 plus t. And there we have it. So I'm just going to plug it in, see what happens. So we have 2 plus 1/2, wait, comma, then ln 4 plus 1/2. Let me do another one. 1 plus t. And we hit submit, see what happens. Hopefully I get it. Nice, got it. Okay. How many more do we have? Okay, we have like 1, 2, 3, 4, 5 more. Okay. Should be chill. Number 7. All right. Yeah, because that's 6. So now here we're being asked to find the point on the curve. Our curve is a vector function, r of t, which has 3 function components, so 4 cosine t, 4 sine t, and the e to the t. Okay. We have a condition where t is exactly in between 0 to pi, inclusive, and the tangent line so we think of derivatives when you think of tangent lines is okay, so it's parallel to the plane. So here now we're given some plane. And the plane is 3x plus y equals 1. And since it's a plane, we know that z equals 0. So, okay, how do we find the point on the curve? So let me think for a bit. Here we're given a vector function that gives us a position. And another piece of information we have here is the tangent line is parallel to a plane. Okay. What do we know about, what can we extract from the plane here? Well, from the plane, we have a point, right? We have a point, and we have a normal vector. Yeah, am I right? I should be right. Let me just double check if what I'm saying is correct. But for a plane, we need a normal vector and an initial point. Yeah, so we need yeah, and then the initial point, I believe. Yeah. So that's what we need for a plane. What else can we say? How do we know if a tangent line is parallel? Well, Um, let's actually draw it out maybe. We have a plane with that equation. Um, we have a tangent line parallel. So when we say parallel, it's maybe a line above here, and then they have the same distance here. Oh, it's perpendicular maybe. So the normal vector of the plane is perpendicular to the tangent vector. That's another thing. How do we do that? Well, we need another vector. We need a second vector to find that thing. So okay, just some stuff that I'm just thinking about. I'm just brainstorming as I go. So um maybe one thing to do here, I mean, it's just finding a point on this curve, but that point has to be where the tangent line is parallel to the plane. Huh. So trying to put the pieces together. So maybe we have a normal vector for the plane. So that's one vector. We need two more vectors. And then we have a tangent line, so that could be a vector. Then we need another one. So maybe the other one is um well, another tangent line. That could be a thing. So we could make two tangent lines, get their cross product, which will give us the normal vector. Um yeah, I'm just thinking about stuff here. Okay, I'm a bit confused. Um okay, let me yeah. So okay, we're given a vector valued function. Um and we're being asked to find the point on the curve, and that point should be where the tangent line is parallel to the plane. Uh, okay. And I guess we need to understand what it means for a line to be parallel to a plane. And so a line is parallel to a plane if its direction vector is orthogonal or perpendicular to the normal vector of the plane. Um, so yeah, we can find the normal vector of the plane, and we're looking for the tangent vector that is perpendicular or orthogonal to that normal vector of the plane. Hmm, yeah, that's how we're going to be able to find it. And so we want to compute that tangent vector. Okay. Uh, and their dot product has to be 0. Oh, oh, this is interesting. Okay. And then we solve for t here. Oh, okay. Okay. Yeah, that's really cool. So here we want to, so based on what I explained, I was kind of getting it, but I wasn't sure. If we have a plane, we have a normal vector, right? Now, we want a tangent vector that's parallel. And if it's parallel to the plane, then that means it's perpendicular, right? And so if this were, let's say, V, this is N, well, we can derive that the dot product of these two vectors should be 0. So that's one thing to note. And here we're going to get something out of t. So actually, I should have just said this is r prime of t, right? If this were r prime of t, then this would be r prime of t. Let me... And then we can solve for t, and then use that t to get a point. All right? So that's our game plan here. So the first thing we want to do is we want to find the normal vector of the plane. Let's denote it as n of the given plane. So let's quickly do that. So here we're given this equation. So it's square root of 3x plus y equals 1, which can actually be rewritten as square root of 3x plus y plus 0z equals 1. And from there we have our normal vector, which has square root of 3. So here we just look at their numerical coefficients. Done. Now what do we need to do? Well, we need to find the tangent vector. So to get the tangent vector, well, we just take the derivative of our position vector here. So we need r prime of t. And if we take the derivative, okay, let's see. So 4 cosine of t. Well, this is just negative 4 sine t. Next one. We see 4 sine t, that's 4 cosine. And we see this other one, e to the t, that's just, oh, e to the t. Cool, done. Now what do we need to do? We find the t value, that will give us a point on the curve. So here's where we use that knowledge that we explained earlier, which was this one. We want to get their dot product to be 0 to find the tangent line that's parallel to this plane. And so if we do that, well, we get this. So we have negative 4 sine t. So here I'm just plotting in what we already know, e to the t. We get the dot product of that with negative, oh no, not negative, square root of 3, 1, 0. And this should be equal to 0. And here I just solve for t. So doing a dot product, so we multiply this thing. So we get negative 4 square root 3 sine of t. We add that to 4 cosine t. Here we multiply by 0. So that's 0. So yeah, we get this thing. Then here we just solve for t. So a way I could do this, well, I could divide everything by 4, right? So I'd get 4. This is tricky. So I could divide everything by 4. So if I divide everything by 4, well, I get negative square root 3 sine of t plus cosine of t. Okay. And then now what can I do? Well, I can put this to the other side. So I can say sine of t, or no. I can say cosine of t is equal to square root of 3 sine of t. Okay, now how do I find t here? That's the tricky part. Um, well, oh, so now I can say we have cosine of t divided by sine of t, which is square root of 3. Let me just switch this. I'll put to the other side so it looks cleaner. It's equal to this. This is just cosine divided by sine is cotangent of t. And so our t is basically our cotangent of square root of 3, which is a number. Now can I find an exact number or no? I don't think so. Okay, but that's cool. But yeah, um, I guess another way we could do it. Actually, I can't think of another way. Yeah, there's one thing I really suck at. It's trigonometry. Okay, but we found our t value that will work. Now what do we do? Well, we just plug in that t value here. Yeah, and then we should get some value out of it. Um, huh. So that's something. Yeah, that is super weird. Um, oh yeah, I could use a reference triangle for this to work. Yeah, I could do that. So yeah, here we have to plug in the t that we know. So now here I just plug in t value to its position vector. So I'm just gonna say it to position vector r of t. And here we go. Now I can't just like plug in sine of. I mean, I could do that. I could do that, but that's gonna look. It's not gonna look nice. But yeah, so I'm basically plugging in r of this thing, right? It's going to be equal to something. But I need to find what this is. It's a point. So, okay, how do I do this? Well, I can make a right triangle. I could say this is some angle t. Um, and then here I have 4 cosine t, 4 sine t, e to the t. So here I can say, oh, we know from here. Let me just put this down. We're going to solve this later. We can say, oh, cotangent of t is equal to square root of 3. What does that mean? Well, cotangent, there was a mnemonics for this, but it's cho, sha, cow. So cotangent is basically cow, the adjacent side of the angle over its hypotenuse. So here we could say this is square root of 3 over 1. And so we can say it's adjacent, it's the side hypotenuse is 1, and we can just use Pythagorean theorem to find the other side, right? The way to prove it's adjacent over hypotenuse, another thing is the SOHCAHTOA. So sine is so opposite So hypotenuse and cosine is adjacent over hypotenuse. Okay, don't mind my handwriting. And we said cosine divided by sine. So that's just going to be this thing divided by this thing. And so if we multiply, so adjacent hypotenuse multiplied by hypotenuse over opposite, cancel. We got adjacent over hypotenuse, we got cotangent. So yeah, just another another way to do this. But yeah, so cotangent, so square root of 3 over 1. Now we can get the corresponding side because we need that. So the corresponding side is just going to be, well, this thing squared. Let's say this is b, I don't know, plus b squared equals 1 squared, which is just 1. So we have 3 plus b squared equals 1. Ooh. Okay. Okay. So we have, I guess we could, oh crap. Is this impossible? Uh, the adjacent, oh, my bad. Now I see why. This should be 1. I forgot. It was adjacent over its opposite. So that should be 1. Then we can find its hypotenuse by just squaring both sides and getting it. So we have 3 squared plus 1 squared equals the hypotenuse. Let's call it c. C squared. So we have 3 plus 1 equals 4, c squared. So c is just square root of 4, which is just 2. So this side is 2. So the thing about the actual trick of sine, cosine, that trig stuff is just using a right triangle. That's a nice way to look at it. And using the mnemonics as well can help. But if not, then that's totally cool. You can use a trig table to do this. Or AI. I mean, you have AI. But yeah. So now that we have this, now we can find what we're looking for. So 4 cosine and 4 sine. So what's that? Well, that's going to be, okay, let's look at it. 4, I think it was cosine, right? Because that's the next. So it should be a cosine. Yeah, 4 cosine and 4 sine. So 4 cosine of t is basically what? Well, cosine is adjacent over its hypotenuse, so it's square root of 3 over 2. Okay, okay. So 4 times square root of 3 over 2, that's 2 square root of 3. So that's our first one. It's way cleaner. Our next one, we have 4 sine of t. So let's solve for that. Well, we have 4 times its opposite over its hypotenuse. So 4 times 1/2, we get 2. And lastly, we have 1 or t. I forgot. E to the t. Oh, no, that one's tricky. Our t is this thing. Maybe you could just use that, right? No harm. You could just say e to the t. You could use that. And that's it. That's my initial point. So my initial point is just this thing. Done. Okay. That was interesting. Interestingly tricky. So let me just go ahead and type that in. If I don't get it, if I do get it, we'll see. Okay, so we use a function. So e to the this is trig, right? Cotangent. Yeah. I want an arc cotangent there. And we have square root of 3 in here. Done. So 2 square root of 3 is my x point. or my x-coordinate, my y-coordinate is 2, and my z-coordinate is e to the arc cotangent of square root of 3, which is again, it's just a number. Yeah, it should be that. Yeah, and if I hit submit, I should get it, hopefully. Nice. Okay. Now we move on to this next one. Yeah, we have 4 more. So let's keep pushing. So for number 8, here we're given curves. So we have curves R1 of t, which is, oh, what's with the handwriting? We have 4t t squared and t cubed. And we also have R2, I believe. So we have 2 vector functions here. This is sine of t. Sine of, okay, I'll put in another thing here. Yeah, usually at the end of the homeworks, this is where the thing gets really long. But we're gonna fight through it. Okay, we have 5t here. And these 2 vector functions intersect at the origin. Yeah, because they're position vectors. And here we're supposed to find their angle of intersection. So when these 2 things intersect, oh, when will they intersect? Wait, you mean curves? Oh, now we're analyzing their curves. So how do we analyze their curves or their paths or their trajectories? Well, yeah, they intersect at the origin. Yeah, we know that. But what's their theta? Their angle of intersection is theta. And we want it in degrees. I watched a video. This guy was trying to find degrees, but he was mentioning temperature, which is kind of funny. Apparently, it's supposed to be too funny. He was talking about temperature because he thought it wasn't math. But anyways, yeah, degrees or radians in angle. Okay, so I guess what we can do here is find their parametric equations, maybe. Oh, another way we can look at it. We have a curve. We have another curve. They intersect at the origin. We have a tangent line. We have another tangent line. So this is their theta. Right? So we can say this is R1. We can say this is R2. We can say this is R1, the derivative. This is R2, the derivative. I just thought of that in the fly. So I guess what we can do here is, so using this idea, well, we need to find their derivatives or their tangent vectors. And we need to find when these tangent vectors intersect. Or honestly, it could even be, yeah, when they intersect at this particular point. But it says it's at the origin. And so the origin here is just 0, 0, 0. Right? These curves are not drawn to scale, by the way. But yeah, this is where they intersect at the origin. So yeah. So I guess hmm, I guess the hard part is finding the t that works. And then the next part is finding what exactly these vectors are, because these are vectors. These are curves. Hope this works. If this works, I'm going to be amazed. These vectors, what exactly these vectors are. And then to find the angle, well, we just use the dot product, because there's a formula for finding the angle for that. But yeah, before we get into that, we need to find these tangent vectors here. So, I mean, I guess the first thing to do is find R1 prime and R2 prime. Okay, let's put T, just so that it doesn't look ugly. Prime T, and the other derivative, the other vector function's derivative. Okay, let's quickly do that. So R1 prime T is just going to be, well, so the derivative of 4T is 4. The derivative of T squared is 2T. And the derivative of T cubed, which is 3T squared. Done. Now we look at R2 prime. Here, R2 prime, so sine T, that's going to be cosine of T. I'm going to do it quickly. Sine 3T, that's 3 cosine T. 3 cosine 3T. So I did chain rule there. And what's this? 5T, right? I think it was 5T. Yeah, so 5T, that's just 5. And once I do that, well, now I want to find what exactly these vectors are. So I want to find a T that works for both of them. So let's do that. So I want to find T value. What does it say? How did I word it? Oh, that will give us point on the curve. Sure, we could do that. That will give us point on the curve. And so here we're going to use the position vectors actually to do this, right? Is that what I did here before? Find T that gives initial. Yeah, see, I use my position vectors because that's where I want to find a specific point. The tangent vectors is when I want to find the direction. So here I want to find the T value first. So I'm going to use these position vectors here, and I'm going to equate them to 0. So I don't know if there's a quicker way. But yeah, basically, yeah, if I make them 0, they should work. I'm gonna guess it's the initial one. Yeah, because they intersect. Yeah, it intersects at the org. Yeah, wait, no. Yeah. So if we do 0, 0 here, 0, 0 here, 0, 0 here, it's gonna work. Because sine of 0 is 0. So that works. Now we want to find, okay, maybe not. Maybe not the t. Because we can already recognize at t equals 0. We'll definitely find that. So I guess I could just plug it in here. Yeah. So yeah, we already have the t, which is just t equals 0. So t equals 0. And then the next thing we want to do is find the derivative at that point for both of these tangent vectors, right? And then we get the cross product of them, and then we can get their angle. So here now we want to find r prime 1 of 0 and r2 prime of 0. Because we want to find the tangent vectors at t equals 0. Okay, maybe let's word it that way. So we find tangent vectors exactly at t equals 0. So let's do that. So you have r1 prime at 0. So here now we're using what we know. So here this is 4, this is 0, this is 0. And then our r2 prime, this is 1, cosine of 0 is 1. This is 3, this is 5. So those are our two tangent vectors. Those are the two vectors here. Now, what do I want to do with these? Well, now I can find the angle of intersection. Now we find the angle. And so there's this fact that getting the dot product of two vectors, well, a formula, and then we get their magnitudes, and then we actually get a theta out of it. So yeah, let's do that. So I'm gonna say, okay, we can get these things here. We get the dot product of both of them, which will be equal to the length of both tangent vectors times the cosine of its angle. And then we just solve for it. So here we have 4 comma 0. Yeah, let's solve for these. So let's first get their dot products. So it's gonna be 4 comma 0 comma 0. Dot product of that would 1 3 5, which is just 4 times 1 plus 0 times 3 plus 0 times 5. So it's actually just 4. Okay, cool. Now we get the length of one of them, or we get the length of both of them actually. So this is just square root of 4 squared plus 0 squared plus 0 squared, well, we get 4. 4 squared, 0 squared, 0 squared, we get 4. And then we get the length of the other one, so it's just square root of 1, square root of 1 squared plus 3 squared plus 5 squared. And this will give me 1 plus 9 plus 25, which will give me 30. Ouch. 35. Can we square root that? No, we can't. Boom. Done. And now we just plug it all in here. So we have 4 equals the length of the first derivative vector. So that's 4 times square root of 35 cosine theta. And then we just solve for theta at this point. So here we have 1 equals square root of 35 cosine theta. And then we have cosine theta equals 1 over square root of 35. And then we can just say theta is our cosine of 1 over 35. And then I just approximate that, says in the question, to the nearest degree. So let me just quickly do that. Okay. So I'll get 1 over 35. I got 80, about 80.3, 80.3 degrees-ish. Oh, crap. Yeah. So that's how I would do it. Hopefully it works. If it doesn't, cool. If it does, great. Let's see. I got points to spare. Let's see if I thought of it correctly. Oh, wow. I am creative. Okay, so that was correct. And then here we do pretty much the same thing. So for number 8, okay, here we're being asked, at what points At what points do the curves R1 of t, which has function components or component functions, t, 5 minus t, and this other one, 48 plus t squared, and R2 t, and this will give me components 8 minus s, comma, what is this? S minus 3, comma, s squared, intersect. So when will these guys intersect? Well, so they give us the paths, right? Now, how will we know if they definitely intersect? Well, again, we just plug them in together, right? So that's how we do it. We just plug them in together and see which points work, right? So when is that? Okay, I wrote D here, which is funny. Oh, this should be S. My bad. But basically, when are these points equal? Right? So let's quickly do that. Yeah. I mean, there's really no other way to look at it. We just equate both of their component functions. So I'm gonna say, yeah, find points of intersection. So it's basically just, okay, R1, points of R1t should be equal to points of R2t. I'm just gonna do them all in t. So I'm gonna say, okay, we have t equals 8 minus t. Good Lord, that's, I don't think that's possible. What do you subtract 8 to something and it still gives you that same thing? Well, okay. 8 minus t is this. Oh, so what can I do with this? Well, I can say, okay, t plus t, so 2t equals 8. And so I get, okay, t is 4. 8 minus 4 is 4. Now let's try that. Do the other components here. So we have, what's this? 5 minus t, which should be equal to, here it's s. We're going to make it t minus 3. Can we plug in a 4 and it will still work? Yes, it still works, actually. So, or we can do it algebraically, but if we plug in a 4 here, 4 minus 3, 1. 5 minus 4, 1. It satisfies. So t equals 1. T equals 4 works. But another way we can do it is we can say 5 plus 3 is 2t. So this is 8 equals 2t. And again, this is 4. So it works for that. And then we can try the last one. 48. So here I'm trying to consider points because there might be more than one t. So this should work. T equals 4. And then this is, I believe, t squared. And then maybe computing it algebraically. So we have 48 plus, or no, not 48. Oh, wait. Huh. See, when you look at this, it actually doesn't make sense. Am I messing something up? Oh. So these don't enter. Huh. Wait. Am I right? S minus 3? Yeah, S minus 3, S squared made a t. This definitely doesn't make sense. When you add it, it's equal to itself. Um, I don't know if that works. Yeah, that one is confusing. Because here, when I plug in the 4, I get 64 and I get 14. So I guess it doesn't intersect, maybe? I don't know. It's not even about derivatives. It's just finding when these 2 points intersect, right? Yeah, so I find that pretty weird in a sense. Um, yeah, that is weird. Yeah, okay, so we set them equal. Um, T equals what works? So for T is equal to 1. Why is it 1? Does 1 work? No idea. Um, okay, so it's okay. How AI did it was interesting, but they turned it into a system. So I guess we could do that. Um, Substitute into third equation. Yeah, that's interesting. Then we solve for s. We get 7. Oh, so we get different t. S and t are different. So they are supposed to be different. Okay. Yeah, see, I found it a bit weird. So yeah, I was mistaken there. So I should treat it like a system. These are different. S and T are different. Yeah, I just realized that. So here we have a system. So we have T equals 8 minus S. Here we have 5 minus T equals S minus 3. And then here we have 48 plus T squared equals S squared. And I basically solve for S and T. So let's do that. So we have a T here, so we can, I guess, substitute. So so I could use the second equation. Instead of T, I plug in 8 minus S. So 5 minus 8 minus S, we get S minus 3. We solve for that thing. So we have 5 minus 8 plus S. We have negative 3 plus S equals S minus 3, which works, right? Now we can continue solving for S. Here we can say, oh, actually we can't continue. What? Huh. So we actually can't continue doing that. But here we can see it works because these are definitely equal. Yeah. So we can't manipulate anything here anymore. Um, Again, we could try popping the t to this third equation maybe. So we have 48 plus 8 minus s here. Square that thing equals s squared. And then we do our little algebra here where we expand 8 minus s. We get 64 minus 8s minus 8s, so that's minus 16s, and then plus s squared. So we have 48 plus s squared minus 16s plus 64 is equal to s squared. And then I can subtract s squared to both sides, so I get, or I could even add these two together. So I get 48 plus 64, that's 112. I get to cancel this s squared on both sides. Minus 16s, I get 0. I get 16s equals 1112. S is 1112 over 16. I get something. 7. So my S is 7. I could then plug it in here. So if my S is 7, then my t, which is equal to 8 minus s, is now 8 minus 7, which is 1. So here my t equals 1. And then I can find points. So yeah, just this is mostly algebra stuff. Yeah. Okay. Let's put that out there. Yeah. So now we find R1 of t. So let's quickly do that. R1 of 1, because my t is 1. So what this is saying is the curves intersect when t is 1 and when s is 7. And so I'm going to find both points. Well, technically they should give me the same point. Yeah. Anyway, so let's quickly do it. So we have R of 1, we have 1, right? That's the point. T is 1. 5 minus 1, so that's 4. And lastly, 48 plus 1, that's 49. Okay, and then we plug in for 2, we plug in a 7 just to see if it works. So here we have 8 minus 7, so that's 1. 8 minus s, so 8 minus 7, that's 1. 7 minus 3, so that's 4. Yeah. And 7 squared, 49. So yeah, they give the same point. So the point that they intersect is 1, 4, 49. Oh, and we're also being asked to find the angle of intersection. Ooh. Yeah, so now we want to find that thing. Well, again, to find their angle of intersection, well, we need to get their derivatives again at that point. So it's the same concept from here. We get their derivatives at that point. So that's where they intersect. And then we plug the point. We plug their parameter. So 7 and 1. And then we find their angle. So it's a whole new step here that we're doing. So that's the extra step. Yeah. Okay, let's quickly do that. So, okay. So the next thing, okay, I'm gonna write the question here. You want to find their angle of intersection. Theta. Let's quickly do that. So let's actually find, so the steps to do that, well, we need to find their tangent vectors. So we're doing everything again, like before. So the additional step was finding this intersection. Yeah. So we need to find their tangent vectors at that point. So I need to find R1 t, the derivative of that. At, okay, let's make it specific. At t equals 1, right? Because that's 1, t equals 1. And s equals 7. So that's the difference between those two. So first we need to take derivatives here. So for r prime 1 equals t. Okay, hopefully this is easier, right? Okay, so derivatives. So we have 1. So 5 become, wait, is this a 5? Oh, it's a t. So derivative of t is 1. 5 minus t, that's negative 1. Uh, 48 plus t squared, that's 2t. Okay, this is easier. And then we take derivative of this next thing here. Now this in terms of s. So here we do 8 minus s, so that's negative 1 for the derivative. Then we have s minus 3, so that's 1. And then we have s squared, so that's 2, 2s. And then we find r prime at 1 and r2 prime at 7. So r1 prime at 1. Well, I just plug it in. So 1, negative 1, those are constants. 2. And then we have r2 prime at 7. This is going to give me negative 1, 1, 14. Because that's 7 times 2, 14. And great, now we have our two thingies here. Now we can actually find their their angle of intersection. So let's quickly do that. So I'm going to get their dot product here. I'm just going to format it. But getting the dot product, and then we get their lengths. And then we multiply by cosine theta, and then we find theta. So to get this dot product, okay, I'm actually gonna, yeah, that's fine. I'm gonna get their dot product. So 1, negative 1, 2, multiply it, negative 1, 1, 14. And this is gonna give me 1 times negative 1, negative 1, plus negative 1 times 1, minus 1. Okay, let me just quickly do it. 2 times 14, that's gonna give me 28. So 28 minus 2, that's 26. So I get 26. Ah, I'm not gonna erase it. So I get 26 here for their dot product. And then for their lengths, oh, now this one's tricky because I go from this length to this point, right? Because that's their length. Okay. But I'm actually gonna check if that's right because I feel like I might, yeah, I might mess it up, but we'll see. Uh, but yeah, my understanding is we got their vector. Now we get the distance from that vector to this point. And we do the same thing for our other tangent vector, R2. Okay. I hope it's right though. Hopefully. Okay. Cool. Um, oh, I don't think oh, so I think my computer died, or GPT died. I guess we'll do it again. Retry again. Or it hasn't. Okay, well, I guess I'll try it myself first. Okay. So yeah, my idea was I'm gonna use that distance formula. From this initial point, the distance of this point, our initial point, 1, 4, 49, all the way to this vector here. So, I really don't. Yeah, that one's super tricky. Oh, I just realized I have to use this vector to get the other point and then get the distance formula of that. Or No, I'm just trying to get the length. Yeah, so I don't need to. Oh, I'm dumb. Yeah, I can just use this like so. Because even if I get 2 points and then get their distances, I get like what? The same thing as this. So I could just use this as it is. Doesn't matter. Yeah, yeah. So this should be chill. Then I get 1 + 1 + 4, I get square root 5. That's the distance of that vector, or the length of that vector. And we do the same thing for R2, R2 prime at 7. And this will give me, okay, we have -1, 1, and 14. So let's quickly plot that in. I could do it that way, but that's going to give me more time. So I don't need to do that. We have 1 + 1 + 14 squared. 1 + 1 + 196, 198. Does that have a square root? Oh, doesn't. Great. Okay. And now I can just plug in everything that we know. So we have 26 for dot product. It's equal to square root of 5 and then square root of 198 and then cosine theta. And then we just solve for theta from here. So we got 26. This is a number. 198 times 5, 990. Can I get the square root of that? I can't. Okay. I was trying to see if I can simplify it. Then I could say theta is arc cosine of 26 over 990. Okay, and then approximately, I put in the nearest degree. So GPT is not working. Let me just do this myself. I got, so 26 divided by square root 990. In degrees, I get around 34.3. Okay, so I'm gonna, yeah, let me see if that's right. I'm gonna stop the video for here because it's too long. And yeah, okay. Um, okay, so I didn't get that right, but I'll come back to it. I'll make another video for it. But yeah, I hope you guys enjoyed. Hope you guys learned something, and I'll see you all in the next one.